data science. It's a great pleasure to introduce Yinglong Guo. He's a graduate student at the University of Minnesota. It's third year. He's going to graduate pretty soon. He is also a full-time data scientist at Meta in the Ads division. And he's going to talk about convergence and generalization for overparameterized neural networks.
Thanks a lot for the intro. And yeah, today I'm very happy to be here and discuss the joint work with Shaohan and Gita on this topic on convergence and generalization for overparameterized neural network. So this is the outline of today's talk. We're going to first talk about some background to make sure we are all on the same page. We're going to discuss briefly about the neural networks basics and have a brief touch about the history, and then we're going to dive into our main theory. After explaining the main theory, we're going to introduce some numerical experiments to show like how this theoretical result can be connected to some of the numerical results. And eventually, if we have some time, maybe we can dive into the proof, technical proof about the sketch, and also introduce some most important lemmas to lead to our main theory. Okay. So neural network is actually, if we jump in a little bit high level, it's one of the most interesting bionic, which means people are trying to study from the animal and invent our own tool, such as we use a radar. It's a kind of a mimicking how bat is detecting the environments. In neural network, we are trying to mimic how our brain is analyzing the bioelectronic signal and try to use this idea to generate an overall method that can take in the input and try to produce any kind of a nonlinear relationship as the output of this neural network. So typically, a neural network will have an input layer, which usually is the most left-hand side, and we will have several hidden layers in the middle, and we will output and we will generate the output layer in the most right-hand side. And a very typical way is that each node in here, or sometimes people call it a neuron in here, is actually taking all the input from the previous layer and do some process and generate a new signal. And then they will pass this new signal to the left-hand side as its own output. In here, I'm picking one of the node or neuron in the second hidden layer. So I call it H2, and I'm counting from the bottom. So this is H2, 4. The signal of this node is actually a combination of all the signal in the previous layer, and we add some like a nonlinear activation function of all this linear combination of all the previous signal that generates the signal in this node, and it will later pass this signal to the later layer. To be more precise, so if we consider an L layer neural network with, let's say, the width of the hidden layer is M, and let's denote P to be the input dimension in the previous example. So P is basically 3. We have a 3 node in the input layer, and we have a 2 node in the output layer. So in this example, the output dimension is 2. And let's denote D as the output dimension. So the input, let's say, is X. That is a P dimension vector. And we will have a series of matrices to help us map this X to an eventual output, which is a D dimension vector. So to put everything together, this is actually how we do this. So when X into there, we first use a matrix to map it into an M dimension vector, and we take a nonlinear activation function. Then we do some linear transformation, another nonlinear activation, linear transformation, so on and so forth. Eventually, we use the last matrix B to map it into a D dimension vector. So in this setup, we made a little bit of simplification that we don't want to train the matrix B and A to make them fixed in there. It's maybe some random matrix, it's totally fine. And our main task is to train all this set of W's, the matrix in the middle, to optimize, to generate a good representation of this neural network. In the other word, alternatively, we can also write the above procedure as a iterative way. So first, the 0 layer, we're actually making it to have the right dimension. And then for each layer, we put an activation function on top of this G vector, and we use the linear transformation to map this previous hidden layer signal to the next layer. And you can imagine in the next layer, you take another activation function to get your own signal, and you pass it to the next layer, so on and so forth. Eventually, your output is again, it's a linear transformation of your last hidden layers signal.
Is it important that you have the same number of nodes in each layer?
That's a great question. It's not important. And in some of the theoretical work, they assume that it's M1, M2, all the way to ML. We want to make this more systematic and simple, so we assume all the layers have a width of n. Yeah. So here we have an activation function sigma. And it's obvious if this sigma is just a linear activation function, say identity, the whole thing is actually not, we don't need this whole complicated stuff because that's as a whole, it's a linear transformation. There's nothing special. So people want to embed some nonlinear transformation inside of it to make this neural network being able to capture all the possible like nonlinear dependencies. So this sigma activation function should be a nonlinear function, intuitively speaking. And typically, not typically, historically speaking, people first use a sigmoid and the tenth function because this is more aligned with the biological stuff. Like our human brain is actually kind of using this bounded signal to be active or deactive, something like that. So initially people are using sigmoid, but later people notice that the sigmoid function have a huge issue in practice because when the input value goes to very large, either side of it, your gradient will become 0. And that is a situation when this neuron will be dead and they will no longer be able to be trained because your gradient is 0. And later we will see how we train it is based on the gradient. So people are thinking about other ideas to make this become an unbounded function. So there are another set of functions which are, I would say, very popular recently. The first one is called a ReLU, or rectified linear unit. So it's basically only taking the positive side and to make it linear. And in the negative side, you just make it 0. But obviously, this function is not differentiable. So you will have some theoretical property which is not preferred. So people are having another approximation to it. It's called a Gaussian arrow linear unit. And this approximates the ReLU pretty well. But we will also notice that in both these two, ReLU or GenLU, the green or blue curves, in the negatives, when you are negative enough, your gradient is also become almost 0. So that kind of sometimes you will suffer again the dead neuron issue. So people proposed another set of activation function called the Leaky ReLU. It's basically to allow you having some gradient in the negative side, but make it different from the slope in your positive side so that you still have a nonlinear function. And also you have a non-bad neuron whenever your input signal is. So, okay, now how do we train? What is our goal to find the best W for this neural network? We want to kind of study it as an optimization problem. Let's say we have a lot of data collected, the inputs and the output. What we essentially want to do is that we want the y hat to be as close as to the y's, so that our neural network is exactly mimicking how the data is working by finding appropriate W's. And in order to find that, we actually is actually trying to minimize this so-called training error. And the training error is nothing more than a sum of all the loss function on each of the data points we collected above. So typical example of this loss function is also very intuitive. Like if we are studying some like a regression task, it's usually MSE. And if we are studying some classification, like y is either 1 or 0, people usually use binary cross entropy as defining here. And if you are doing some categorical, there are some categorical cross entropy, so-called CCE. There are many different choices of this loss function. In our talk, we were mostly talking about the regression task. So the MSE loss function is our choice. And in order to find this optimal W, of course, we need some initialization. actually, initialization is not very related to our topic, but I still want to mention. People nowadays, I think one of the popular choice is He's initialization. It's basically to ensure your signal in each layer will become kind of consistent, and there is no growing, exploding of the variance of your signal in the initial step. And of course, there are some other choice of initialization method. After you initialize all the W, you need to choose one of the optimization method to tune your W. Eventually goes to a best result. Some common method are gradient descent or stochastic gradient descent, and there are also some other variates such as Adam and so on and so forth. But today we will mostly focus on gradient descent and or stochastic gradient descent. So for gradient descent, I think all of you will be very familiar with it, but just let me clarify what do we mean. We first initialize a W0, and we want to choose a certain learning rate. Usually it's very small, eta. And for each time, we update the parameter W following this fashion. And actually, if we define W to be a set of W, this definition may be not 100% accurate. So just to clarify, what do we mean by gradient W of L? It's actually mean a set of gradient with respect to all the W in each of the layer. So gradient of a W1 with, the gradient of W1 on L and the gradient of L with respect to W2, so on and so forth. And when we do that update, it basically means we just change the W in each of the layer. We just change the WL in each of the layer correspondingly following this fashion. Okay, so for the SGD, stochastic gradient descent, the stochastic part coming from like what is the L? We are calculating the gradient. So in the gradient descent, the loss function, the training error L is actually the sum of loss function of all the samples. So in the stochastic gradient descent, we just change it to let's say LB. It's the sum of the loss function in a subset of all our data set. And this subset is chosen randomly at each step. That is how the stochastic part coming from. And instead of using the gradient of L with respect to W to update the parameter, we use the gradient of LB with respect to W to update the parameters. Okay, do we have any question regarding our quick discussion of the basics of a neural network? Okay. If we are all good about it, we're gonna move to like a little bit of discussion about neural networks history and see how the recent development is happening, and also touch base to some like existing theoretical work. And that will lead to our theoretical work. So the neural network have a different types. Like the previous one I introduced, it's so-called a fully connected neural network, because every node in the previous layer are connected to every node in the next layer. So that's called a fully connected neural network. And people later notice that if we do that, we have a huge amount of parameters that we can train inside of it. So it usually leads to some overfitting or some issue. So people developed several different variants of that. It's usually, you can regard it as a fully connected neural network plus some modification, restriction, or parameter sharing. And some very famous ones, including like the convolutional neural network. It's proved to be a huge success in handling image data. Recurrent neural network and the transformer, they are also proved to be a huge success in handling the natural language processing text kind of data. And a quick summary, it's a very high level summary about how neural network developed. Before 2000, like a fully connected neural network is only like a competitive performing with all the other traditional machine learning methods, such as tree-based algorithm, including XGBoost, AdaBoost, all those methods. And in the last 10 or 1 decade or 2 decades from today, the convolutional neural network start winning a lot of image classification tasks, and the recurrent neural network, together with some transformer architecture, wins a lot of the text classification tasks. And I'm citing several like a typical neural network in those categories for CNN, like a VGG19. The number I cited here is the number of parameters it contains. So there are 144 million parameters it needs to train in order to do a good job in classifying all the images. And for RNN, you can see the number is growing. And recently, we all know like the large language model is starting like draw a lot of attention, and they can generate some very useful conversations, including like generating codes and so on and so forth. I don't remember which version I'm citing, but one of the versions for ChatGPT, it actually contains 1.4 trillion parameters. So you can see the parameter number is actually growing very rapidly. If I cannot claim this is exponentially, it is still growing very fast. And there is actually some interesting phenomenon that researchers noticed that the number of a parameter is actually the driver of having this ChatGPT to be that clever and being able to produce useful conversation. And this is so-called this double descent phenomenon. So I don't remember this, this figure is from Wiki. I don't remember this is based on a real simulation or it's only a conceptual idea, but the x-axis, it reflects the number of a parameter, and y-axis reflects the error. The blue dot reflects the test, the blue dot reflecting the training error and the black dot reflects the testing error. So if we only look at the first half, this is more traditionally understanding the so-called overfitting. When you are increasing the number of parameters, your training error will be reduced very fast, but your testing error after a certain point will start increasing. That's because you are overfitting this model. In the other word is that your model is actually learning each of the data point instead of learning the underlying relationship. But researchers find on the second scenario, if you further increase the number of parameters, this testing error will start decaying again. And in this region, it's actually where why this ChatGPT model start like gain attention by introducing more and more parameters, because we are expected to see, we identify this phenomenon that the generalization or the testing error will also continue to decrease when you are further increasing the number of parameters. So this.
Sorry, what's the cutoff with the vertical line? I think like the
I kind of feel this figure is only a conceptual figure. Okay. So we are just trying to say there is a cutoff in there.
Okay.
Yes.
Is this picture really only true if you have the large training sets? If you give a small training set, you expect it to picture this.
Yeah, I think this will depend on large training sets. Thanks. Yeah, thanks a lot for clarifying. Yes. So our goal or theoretical goal in here is we want to develop some theory for this, ideally for this regime, to capture what will happen in the overparameterized neural network. And as we see above, actually the first question is that whether or not this convergence will happen, because that's actually in some scenarios that's still a question mark. It's not overall speaking understand already. And the second is that whether the testing error will decay as we found in this general, in this phenomenon. Okay, now we go back also to check like what is kind of a history of our convergence theorem for overparameterized neural network. In 2015, there are works that showing numerical experiment can find that overparameterized neural network can actually avoid a local minima and converge to a global optimal solution. Now, maybe it's good enough, right? We already find this numerical evidence that overparameterization is a good thing to have. But just like once we know the plane can fly, we still want to study the aerodynamics to make sure this flying is have a scientific ground. And also, I think more importantly is that by studying the theoretical part, we should be able to guide how to improve the plane and make it fly better. So similar logic in here, people continued like the theoretical development. I think first in 2018, there is a very theoretical work is showing that when the width goes to infinity, and when you are using some smooth activation function, then the training error, if we are using MSE, will converge to 0 when you are updating the coefficient by gradient descent.
So I have a question. When you mentioned the overparameterized neural network, the wide local minimum, you're releasing when you do the training procedure, the dynamics of why this. What is that? Why?
Yeah, it actually means the overall training error can converge to the minimum possible training error. So I think actually it narrows down to when you are over-parameterizing the space, you will have a lot of a global optimal in that huger space. So it's actually making it easier to find a global optimal in there. But we will see some of the result later. Maybe that can address that.
Oh, but another question is, does it know that how many local members for a given neural network? Okay, let me rephrase the question. Is it know the number of how does the number of local members depends on the size of the parameter of the neural network?
To my knowledge, I don't know something on that front, but I think this is an interesting question. Yeah, how many local minimums are there actually? Yeah.
Is it even known if are local minimums what's over or is there I don't know.
Yeah. I don't feel there is no local minimum. I think they are still existing because all our existing theorem is actually with all the theorem state as with the probability that we're gonna converge to zero. And I think that probability is used to avoid some of those local minimums. So I don't know the real answer to that, but my intuition is that in the overparameterized regime, the local minimum become much more sparse in
this numerical node we just mentioned, the parameter, the neural network is got to overparameterize the local level.
Oh, no. Sorry, this is only my intuition. I'm sorry.
Okay.
It's my guess. I should say my guess. Numerically, people find this conclusion like they can avoid a local minimum. So I think it's
it doesn't say that.
Yeah, it doesn't say it's more sparse.
Are they able to find like there's where people find that?
Yeah, because usually global. Yeah, usually sometimes global minimizer will have a issue about overfitting, and sometimes local minimizer is preferred. But I think that's only I don't feel that's a real thing unless you included some adversarial like a training procedure to make it more realistic. Otherwise, if you are kind of artificially select a point to stop and your training error is not smaller, and you just said that one empirically speaking give me lower testing error, I think it's just a compromise. It's just because we didn't understand that completely, so we find an early stop can give us some advantage. That's my understanding, but yeah. Okay. And if we continue the journey, not very long later, we have another theorem, because previous one, we obviously require m goes to infinity. That's something very unrealistic. And so next work we can get is that when m is sufficiently large, and also with a smooth activation function, we can also show the MSE converge to zero with a gradient descent. And further, the smooth activation function is also not very popularly used, and ReLU is more like a commonly used activation function. So by continue this journey, we can also show when m is sufficiently large, and when using ReLU activation function, the training error can converge to zero using either gradient descent or stochastic gradient descent. And of course, something I didn't write down is that what is the order of a requirement for m is actually also keep improving. Like people can make this sufficiently large to be smaller and smaller. And if I recall correctly, some recent work even goes to make this sufficiently large m to be linear or even sublinear to the data sample. Like in this work, the result is m is polynomially dependent on n. So our research focus in this talk, we're gonna focus on overparameterized neural network. So the width or the n gonna be sufficiently large. And we will focus on regression task. We're going to use MSE as our loss function, but we will also make an extension to cover all the convex loss function, which we will potentially talk later. And for the activation function, we consider a class of activation function, and we consider ReLU. So this is a class that we can tune the different alpha so that we can recover, or we can get a different kind of activation function. And of course, when you choose alpha equals to 0, that recovers to ReLU. And our main result is about the convergence error and the generalization error, and we hope to make it dependent on alpha. And this is one of the kind of philosophy of our work. And also our work. We think like it is important to keep improving the order, right? That's definitely some significant work, but knowing that it's really not helping us guiding the practical work. Okay, we know when M is sufficiently large, it can converge, and we know the sufficient large can be even smaller and this converge. That is not really helping the practical work, because in practice, you can always use some like a cross-validation to make sure your neural network is good enough. And they can choose the width according to some like cross-validation or different method to choose their width to make sure it is converging.
But this story is for fixed advance, or you also like this?
That's a good question. I think these two are all allowing depths to be L. I don't remember this work. I think it also allows the depths to be L for any depth.
Oh.
Yeah.
But L is fixed.
Yes, it's a fixed number. Yeah. Because there are.
Yeah. But yeah, so that's M.
Yeah, M is a width. Yeah. Depth is a fixed number, because there are also some work focused on like a 1-layer or 2-layer neural network, and probably you can get a better order in that particular scenario. But in those, at least these two work is definitely for any fixed L. I don't remember this work. I think it's also for any fixed L. Okay, so we want to study on this class of Leaky ReLU is also because we want to see which choice of alpha will get our optimal theoretical result. And in this way, it becomes a more actionable result, because we can come back to the applications and say, instead of randomly choose an alpha 0 or maybe small positive, we should choose this number because theoretically we can find it have certain advantage. That is kind of the thinking process of this work. Now, before going to the main theory, of course, every theory will need some assumption. So in our work, our major or only assumption is that we need a data separation. Like our input data should be separated at least by a small constant delta. On the other word is that we don't have two identical inputs in our training data, which I think it's a reasonable assumption. And in our training process, we want to set an objective in it. So we want to train the neural network so that the training error becomes smaller than this given constant epsilon. Okay. Now next is our like convergence theorem for gradient descent. It says that when the M, again, M is the width of the neural network, when it is sufficiently large, and when we are using gradient descent to train this neural network with a small enough training step, the eta is a learning step, then we have then with a high probability, this probability goes to 1 when the width of your neural network goes to infinity. So we can say this is a high probability. We know that the training error at a t step will be smaller or equals to t's power of a gamma to the training error at the L step. And up to the capital T, the training error will be smaller than epsilon. And of course, capital T is calculated based on this linear convergence. That's pretty simple. And the most interesting part, in my opinion, is that this upper bound of our training convergence rate, gamma, is dependent on alpha, this red part, so that we can see when alpha equals to 0, or you choose a different value of alpha, the upper bound of your training of your convergence rate will be different. And then the natural question is that which choice of alpha will actually give us the smallest upper bound of our training of our convergence rate for the training error, right? Before that, we also have a very similar result for stochastic gradient descent. You might notice that some of the parameter or some of the orders are different, and we need a small b here. The small b is capturing like the size of that subset b being used in the stochastic gradient descent, but eventually the result is similar. And this, our upper bound for the convergence rate, if we call this is a gamma dependent on alpha, I'm sorry, just to clarify in here, all the other things together will give us a constant once we fix the choice of everything else, right? So the other things are all constant, and the only dependence alpha in that expression, actually the function looks like this way. So we first want to look at this function, and I want to give you some intuition, or maybe gives you some sanity check. Let's say when alpha goes to 1, what is the situation in there? The activation function actually becomes a linear function, right? And as we know how neural network works, when you have a linear function, it actually is a linear relationship. So it's impossible for you to approximate any relationship. And here, our gamma, when alpha equals to 1, goes to 1. That means that, okay, we still have a training error bound, but that bound tells you nothing. It cannot converge to 0 at any like training step. So that makes sense, right? Now we have a lower alpha, like people usually choose ReLU that is corresponding to alpha equals to 0. And let's think about another scenario when your alpha is converging to negative infinity. In that case, if you look at that function, the value will also converge to your value of ReLU. And why is that reasonable? I think I forgot to include a figure in there, so I will just use a blackboard. The ReLU function looks like this way, right? And when your alpha goes to minus infinity, your function will actually look like this way. In the negative side, it's a huge slope. And in the positive side, you have a linear function. And if you rescale it, consider your negative side's coefficient slope goes to negative infinity, you will actually get something like this. And the positive side, because it's a constant slope, right? It actually can be considered as approximating to this line. So in this way, you're thinking about it, the alpha goes to minus infinity case is actually the activation function converges to the inverse of the ReLU. So intuitively speaking, the bound of this convergence rate should give you the same value, and it does. Now, the last thing is that, okay, the minimum point, and we can find that, interestingly, when alpha equals to -1, actually gives us the smallest upper bound for our convergence rate. And alpha equals to -1 is actually corresponding to absolute value function. So in the other word to say is that based on this analysis and the derivation, we can say the upper bound for the convergence rate of the training error reaches the smallest when you are using absolute value function out of the class of Leaky ReLU. This is a convergence part. Now we move to the generalization. Before doing that, we want to first quickly define what is a generalization error.
He asked you before about the L, the number of layers, and maybe it's good to say something, that you don't see any dependence. L, gamma.
Oh, yes. Yes. And actually, this is a good point. I think we all, comparing to the previous result, we also had some minor improvement about the orders in here. I remember one of them, the order depending on n is a 6 or something. But in my opinion, these are less improvement. Like the major thing we want to say is that this theorem can help us guide some choice of the alpha in the application. And I recall one of the previous work, the gamma here have some L in the denominator. That basically means that if you have a larger or deeper neural network, your convergence might be slower, which might be a bad thing for the deeper neural network to be used in the practice. And in our work, we actually excluded that dependency. So the convergence is that does not depend on the depth of the neural network. The upper bound of the convergence doesn't depend on the depth of the neural network. And actually, I just noticed I'm running out a little bit about the time. So I will skip a little bit of discussion about our generalization error. But the generalization error is defined as this way. The expectation of our MSE if we are drawing the data from certain underlying distribution. And the generalization error actually looks very ugly, very complicated in here. And the only thing we can say is that when t is small, which means the early stopping time when our training epoch is smaller, then the major thing dominates this upper bound of generalization error will become this part. And again, it's basically the training error. So that, again, alpha equals to -1 corresponding to the minimum upper bound for this one, but only when t is small in the early stop regions. Okay, now initial question is that, okay, we showed some theoretical result, and that is only an upper bound result, right? It's not, we don't have a lower bound conclusion. So it means, so we want to kind of demonstrate whether the convergence is really aligned with what we showed before, and whether -1 is really an optimal choice. So in order to do that, we conducted several different numerical experiments. The synthetic data, we just randomly created some nonlinear dependency of y of x. And second, California housing. This is based on all the house information, like square feet, their location, so on and so forth, try to predict their house value. And there are also some other image-related data set of FMNIST trying to categorize an image, a gray image. I think it's 32 by 32. And the CIFAR10 is a colorful image. We're also trying to classify it in into 10 different categories. And the last one is text data. It's based on some text review, and we want to determine whether this review is a positive or negative review. So, so in this one, like we said, the theoretical convergence upper bound and our empirical convergence rate alpha, our empirical convergence rate gamma, we want to check whether or not they are aligned. And we first one, we are running this on the regression task for the synthetic data in the left-hand side and for the California housing data in the right-hand side. This orange line is our theoretical upper bound of our convergence rate. And the blue line is the empirical convergence rate we observed based on training error in the training process. So we basically find when we are changing different alpha, actually this empirical convergence rate is actually aligned with our theoretical upper bound very well in the sense of shape. For synthetic data, it matches very well. For the real data, it's not as good as the left-hand side, but it also, the trend looks very similar. Now, the next part is that we change different alpha and we want to compare their training error in the real situation. So in here, the x-axis is the number of epoch and the y-axis is the error. For the left-hand side, we are looking at the training error. So it is pretty obvious, here is looking at the synthetic data. So it's pretty clear that when alpha choose -1, the convergence of training error is obviously the fastest one. That aligned with our theoretical upper bound. And for the left-hand side, we're looking at the testing error. And as our theoretical result indicate, we're only looking at early epoch, and we can find at certain point, the alpha minus 1 actually is better than the other choices. And we can also verify this in the California housing data set. The left-hand side is training error, right-hand side is testing error. And before we're running into the other data set, like those data set are more about classification. We want to talk, our result can be expanded to other loss function. Whenever the loss function is a convex function, such as binary entropy or cross entropy, or some other choice of this square arrow, those are all convex functions. So our theory can be expanded in this following way. If we look at the upper bound of the convergence in here, mostly it's similar. The only difference is that it actually depending on the arrow on your current step. So at each step, you can say the alpha equals to -1 give you the smallest upper bound, just as before, but it's not longer a linear convergence because you have an arrow in here. Like when that arrow goes to 0, your convergence rate is also goes to 1. So in here, you didn't see very nicely shaped linear convergence, but we can still tell in the left-hand side, this is for the FM mist. In the left-hand side, the alpha equals to -1 gives us the fastest convergence in the training arrow. And in the testing arrow, again, in the very early epoch, we can find alpha -1 have some advantage. And there are some other data kind of telling the similar story. This IMDb data set is performed a little bit ugly. But in the left-hand side, the training arrow, we can still tell alpha equals to -1 give us the advantage. The right-hand side, the testing arrow, we didn't find a similar story. But this is currently our numerical result. I think we don't have enough time, so I will not go through our proof sketch, and I will end here and see if we have any questions.
Until you have 7 minutes, yeah. Yeah.
But yeah.
Well, so the last couple of days we actually had this in practice. Would use CNNs to use or
Yes. I recall we use a CNN.
Your supply.
Actually, yes, that's a great question. Our theory only applies for fully connected neural network, but the CNN is just a fully connected neural network allowing some parameter sharing. And we didn't dive into that case, but I think it can be extended with some extra work.
Well, another question is that the Leaky ReLU was really implemented as 2 ReLUs, right?
Or some together, yes.
Yeah, some together. So, yeah. But I guess when you train the training, that would be different than doing training. Maybe that works.
Yes, yeah. It's equivalent, but you need, like you said, you need a double width, and you need to fix some of their parameters relationship in order to reach the same effect. So it might not violating the theorem because in here we are, I'm sorry, for example, the convergence part, we are fixing the number of m, and we got a certain convergence rate. But if you increase the number of m, and if you let alpha equals to 0, probably that's get you another upper bound that is also smaller than your smaller width. So yeah, I think that's kind of consistent with the theory.
Interesting to get the absolute value function. Is that a widely used activation function?
Actually, we didn't find too many use of absolute value function as a activation function, and but from our perspective, I think that's the reason we do theoretical work, right? We want to find something that might be useful for the application while people intuitively didn't use in real world. Yeah. Oh, yeah. Oh, yes, yes. That is so the question, if you didn't see it clearly, is asking like why the result for the IMDb is not as good as the other numerical simulation. I think one reason is that IMDb is natural language processing data. They have reviews in there, and you want to extract the you want to categorize whether it is positive or negative. So the first step in handling that data is to have an embedding layer to map each of the English word into a high dimension vector. I kind of feel from that step to the aggregation step, we are actually losing some information comparing to the other data set. So my current intuition is that that is the reason for not having the very similar performing result. But yeah, thanks for the question. No, we are using an embedding layer and then aggregate for each of the paragraph, and then use a recurrent neural network. Yes, that's also true. Yeah, recurrent neural network actually is much different from convolutional neural network because it's architecture. So yeah, thanks a lot for reminding me that. And that's probably another reason for we didn't get a similar optimal convergence rate. For the testing error, yes. Yes.
And they also
yes, it's overfitting after that number of epoch it become increasing. Yes.
But for testing, we only have guarantees for very small number of users.
Yeah.
But the other ones, they don't seem to overfit.
I remember for some of them, actually the testing error will also like bend up eventually. Yes.
These curves also very smooth. Did you average this over many months, or is it just a single trial?
Oh, this is actually several trial and average events. Yes. Yeah.
Practical purpose, we recommend use name for the
that's a great question. I would say we at least need to include alpha equals to -1 as one of the searching space when people are trying to find the optimal solution, optimal architecture. Because in the theorem, like we really need to say this is a overparameterized neural network, and it should be a really overparameterized one. So in practice, that's probably sometimes not feasible especially if you are dealing with some small data set. So at this point, I would just say we should include alpha equals to -1 as one of the options in architecture search. Yes. Yes. What do you mean when in the experiment we have a different rule?
I think you have this experiment. It means that if you check cases where the width is not so high, and is this phenomenon alpha equal -1 is optimal, was also true when n was not.
Oh,
that's what we meant, right? The observation is not so small.
Oh, okay. So, first part, if we don't have the neural network to be large enough, in some data set we are also tested with a narrower neural network, and we didn't find this phenomenon. And second, we actually didn't try different initialization approach. We always used that Hurst initialization.
So what other initialization?
So do you mean it's like using a uniform distribution for initialization?
Yeah, there's a hidden scaling time. Scaling. From up for that. Scaling. After that, you just. Here's what you see.
Yeah, yeah, in current one, we actually only tried this way, but it would be interesting to try other. Mhm. Yeah, thanks.
The-
Oh, we used the SGD. Yes. Yeah. Yeah. Actually, yes, our theorem also didn't expand to Adam or other approaches. At most, we expanded to SGD. Yeah, I don't know. Intuitively speaking, I think maybe theoretical result might give us similar thing, but it will need may have some different parameters over there. But yeah, I don't know. I think it should give us similar conclusion. Yeah, that's also a good direction. We can try that numerical experiment.
Complex function. We have dependence on L.
Yes.
You think that the possible
I can't answer it right now. I need to check yeah, I need to review the proof to see if that's.
But from the numerical experiments, is there anything different when for different one?
Oh, you mean the depths? We didn't. Yeah, we didn't run too much like a variation of depths in here because that's not our major theoretical result. Thank you. Thanks. Should I stop recording? And
Is it still recording, by the way?
yeah, it's still recording. Thanks.
Yeah, so then.
Okay.
Yeah, so that number is what I would see.